Welcome to the Deep Dive. We're the show that goes deep into complex topics, tries to cut through all the noise, and basically gives you a shortcut to being truly well-informed.
That's the goal.
And today, we're really plunging into the incredibly dynamic and fast-moving world of artificial intelligence and machine learning.
Yeah, it's everywhere now, isn't it?
It really is. And we're not just talking about, what AI is, but maybe more importantly, how it actually learns.
Yeah.
What can it do? And what are the, frankly, profound questions it's raising about, well, all of our futures?
That's right. And for this deep dive, we've gone through sources that really give you a solid foundation. The building blocks of AI, you could say.
Okay.
Plus, we're looking at the really big questions that the top researchers, the people really in the trenches, are grappling with right now.
So we're pulling out the key stuff.
Exactly. Extracting those nuggets of knowledge, the key insights, giving you that shortcut, that path to being well-informed without drowning in, all the technical details.
Absolutely. Our mission here is pretty clear. Cut through the noise, demystify the jargon as much as we can, and give you that shortcut to really understanding what's going on with AI.
The core principles of machine learning.
Okay, so let's unpack this first bit. Machine learning. At its heart, it's the part of AI where the algorithms, the computer programs, they kind of learn by themselves, right? They improve by looking at data.
That's the core idea, yeah. It's quite remarkable. Think about supervised learning specifically. The main goal there is to build a model.
A model.
Right. And this model takes some input. We often call it a feature vector, which is just, a list of characteristics about something.
Like height, weight, age for a person.
Exactly. Or the words in an email. And then it uses those features to output some information, like a prediction or what we call a label.
Oh, okay.
So it could take that person's medical data, their features, and predict, say, their probability of having a certain disease. Or it could look at the features of an email, the words, the sender, and predict if it's spam or not.
Okay, so supervised learning sounds like you're basically giving the AI a study guide with answers. Like, here are photos of cats, and they're all labeled cat. Here are dogs labeled dog.
That's a great analogy. You provide the examples and the correct labels. The system then learns to find the pattern, the predictor, that connects the inputs to the outputs.
Got it.
And that's really different from unsupervised learning. There, the data, well, it has no labels, no answer key.
So it just has to figure things out on its own.
Precisely. And that's why many researchers see unsupervised learning as, well, one of the most promising ways forward for AI. The idea is to have systems that can learn patterns and structure just by observing the world, without needing humans to label massive amounts of data.
Which sounds amazing.
It is. But it's also incredibly difficult. It's one of the biggest challenges the field faces today. Finding meaningful structure in unlabeled data is hard.
That makes sense. So, okay, whether it's supervised or unsupervised, once you feed it all this data, how does the machine actually, learn? How does it adjust itself to make better predictions? How does it find the right settings inside?
Right. So machines are actually very, very good at solving what we call optimization problems.
Optimization.
Yeah. They continually tweak their internal parameters. You might hear terms like weights and biases in neural networks to try and minimize some kind of error, like how far off was its prediction, or sometimes to maximize a reward.
So it's constantly adjusting based on feedback.
Essentially, yes. But here's the really crucial part. The true test isn't just how well it does on the data it trained on. That could just be memorization, right?
Like cramming for a test you already have the answers to.
Exactly. What we really care about is how well it performs on new data. Data it's never seen before. We call this a holdout set or a test set.
Ah, okay. That's the real measure of learning.
That's the real measure. This is why we always split our data. Typically, you might use, say, 70% for training the model, 15% for validation, that's for tuning things during development, and then a final 15% for the actual test set, purely for evaluation.
And the proportions can change.
Oh, yeah. If you have enormous data sets, like millions of examples, maybe you only need a tiny fraction for validation and testing, like 95% training, 2.5% validation, 2.5% test.
And I guess this leads to that problem you hear about called overfitting.
Absolutely. That's a huge one.
Is that where the model gets too good on the training data? Like it learns all the little quirks and noise, not just the real pattern.
You've got it. It learns what it observes in that specific data rather than the underlying concept you, the human, actually care about. It picks up irrelevant details, statistical flukes.
It's like your animal example. If all the training photos have blurry backgrounds, it might learn blurry background means animal.
Precisely. It fails to generalize to new situations. So thankfully, we have ways to combat this.
Okay, good. What are they?
Well, you could try a simpler model type, maybe one that's less flexible, less likely to wiggle around and fit every single data point perfectly.
Like using a straight line instead of a super curvy one.
Kind of, yeah.
Yeah.
Or you could try reducing the complexity of the input data, maybe use fewer features. Adding more relevant training data, if you can get it, is often very helpful too.
More examples help it see the real pattern.
Right. And then there's a whole toolbox of techniques called regularization. These basically add penalties to the learning process to discourage the model from getting too complex and just memorizing.
So things like L1, L2 regularization, I've heard those terms.
Exactly. And things like dropout in neural networks, where you randomly switch off parts of the network during training to make it more robust. Also techniques like batch normalization or early stopping the training before it starts overfitting.
Okay. And what about just the practical side of getting the data ready before you even start training? I imagine you can't just dump any old data in.
Oh, definitely not. Data preparation is, well, it's fundamental and often takes up a huge amount of time in any real-world project.
Why is that?
Well, for one thing, many algorithms, especially those based on, linear algebra, they really want numerical feature vectors, numbers.
But data isn't always numbers, right? Like categories,
Yes.
colors, days of the week.
Exactly. So you need ways to convert those categorical features into numbers. A super common technique is called one-hot encoding.
Voyage!
Yeah. Basically, if you have categories like red, yellow, green, you turn that into a vector of zeros and ones. So red might become 1, 0, 0, yellow 0, 1, 0, and so on. Only one position is hot or 1.
Ah, clever. And missing data. That must happen all the time.
All the time. And you have choices. If you have tons of data, maybe you just remove the examples with missing values.
Just discard them.
Yeah, if you can afford to. Or use data imputation techniques. That might mean filling in the missing value with, say, the average value for that feature across all the other examples. It's not perfect, but it can work.
A deep learning revolution.
Okay, so building on those machine learning basics, the last decade or so has just been dominated by this thing called deep learning. That's where AI really started hitting the headlines, wasn't it?
Absolutely. Deep learning, powered by deep neural networks, is behind, well, the vast majority of the really dramatic advances we've seen recently.
And neural networks, they sort of inspired by the brain, loosely.
Very loosely, yes. They roughly try to emulate the structure and the way biological neurons interact. The simplest unit is something called a perceptron. Think of it as a very basic simulation of a neuron.
Okay.
It takes several numerical inputs, each with a certain weight or importance, adds them up, and then produces an output, often just a binary yes-no or a 0-1.
And the deep part, does that mean it's thinking deeply?
Huh, not quite. It's less philosophical. Deep just refers to the fact that these networks have many layers of these simulated neurons stacked on top of each other.
Lots of
Lots of layers. And crucially, there are nonlinear functions between these layers. Without that depth and nonlinearity, they couldn't learn the really complex patterns that make them so powerful.
And this wasn't always the dominant approach, was it? I feel like neural nets had a bit of a winter.
Oh, absolutely. It's been a real roller coaster. There was huge excitement back in the 1950s and 60s. But then, partly due to some influential critiques pointing out limitations of simple networks.
Like from Marvin Minsky.
Exactly. Neural networks kind of fell out of favor for quite a while. Research funding dried up. It became a bit of an AI backwater.
But then they came back.
They came back in a huge way. A key development was an algorithm called backpropagation. It sounds technical, but it basically provided an efficient way to train these much deeper, multi-layered networks, figuring out how to adjust all those weights throughout all the layers.
And wasn't there something about data and computer chips, too?
Definitely. Two massive catalysts. First, big data. Suddenly we had access to enormous data sets, especially from the internet.
Like images, text.
Millions, billions of examples. And second, the rise of powerful graphical processing units, GPUs.
The things gamers use.
The very same. It turned out their architecture, designed for parallel graphics rendering, was incredibly well suited for the massive parallel calculations needed to train deep neural networks. It made training feasible on a scale that was impossible before.
And competitions like ImageNet really showed this off.
ImageNet was a huge turning point for computer vision. Suddenly, systems using deep learning, specifically convolutional neural networks or ConNets, started smashing previous records for image recognition.
Convets. What's special about them?
They're designed specifically for grid-like data, like images. They have layers that learn to detect features hierarchically. So early layers might detect simple edges or corners.
Okay.
Later layers combine those to detect shapes like eyes or noses, and even later layers combine those to recognize objects like dogs or cats from those millions of ImageNet photos. It's kind of analogous to how our own visual cortex seems to work.
Fascinating. So that's images. What about language? How does deep learning handle text and speech?
That's another huge area. For sequential data, like a sentence of words or audio over time, we often use recurrent neural networks, or RNNs. They have connections that loop back, allowing them to maintain a kind of memory of previous inputs in the sequence.
So they can understand context.
They try to, yes. And a really insightful development within language processing was word embedding learning. Things like word2vec.
Word2vec.
Yeah.
Yeah.
Instead of us telling the machine what words mean, the machine discovers relationships between words by looking at how they're used together in huge amounts of text.
How does that work?
Basically, if words like book, paper, and article frequently appear in similar surrounding contexts, like next to words like read or wrote, the system learns that they must have related meanings. It represents each word as a vector, a point in a high-dimensional space. And words with similar meanings end up close together in that space. It's really clever. And it can even capture analogies. The famous example is that the vector for king minus man plus woman ends up very close to the vector for queen.
Whoa, just from reading text.
Just from statistical patterns in text. It's not true understanding, but it's powerful pattern matching.
And I guess this flows right into things like, Google Translate or question answering systems like IBM's Watson playing Jeopardy.
Exactly. Modern machine translation often uses what are called encoder-decoder architectures, frequently built with RNNs or newer variants like transformers. And some companies have claimed human parity on certain translation tasks, though that's debated.
And Watson.
Watson winning Jeopardy back in 2011 was a landmark moment, a huge PR success for IBM. But within the AI community, there was definitely debate.
Why? It seemed amazing.
It was amazing engineering. But some argued it wasn't necessarily a huge leap towards general intelligence. It was highly optimized for Jeopardy's specific clue structure, trained on, I think, hundreds of thousands of past clues. Was it true understanding or an incredibly sophisticated pattern-matching parlor trick? The jury's still somewhat out on its broader implications for AGI.
Okay. And we have to talk about games. AlphaGo beating the world Go champion? That felt huge. How did that work?
AlphaGo was a triumph for another type of machine learning, reinforcement learning, or RL.
Reinforcement learning. Different from supervised.
Very different. RL doesn't need labeled examples like supervised learning. Instead, the system, the agent, learns by trial and error in an environment. It gets intermittent rewards or penalties for its actions.
Like training a dog with treats?
Kind of, yeah. It's inspired by operant conditioning in psychology. AlphaGo learned to play Go largely through self-play.
Playing against itself.
Millions and millions of games. It started out knowing just the rules, played randomly, and gradually figured out which moves led to better outcomes, which board positions were more valuable, refining its strategy constantly.
And it came up with moves humans hadn't thought of.
That was the incredible part. There was this famous move 27 in its match against Lee Sedol. Initially, human commentators thought it was a mistake. Just bizarre. But later, they realized it was a deeply strategic, even beautiful move that reshaped the game. It showed that AI could not only match human experts, but potentially discover entirely new knowledge.
Okay, this all sounds incredibly powerful, almost scary powerful, but are there limits? Where does this deep learning intelligence still fall short of, actual human understanding?
Oh, absolutely. And researchers are very upfront about these limitations. It's crucial to understand them. One major one, maybe the Achilles heel, is the massive reliance on data, usually human-labeled data.
Right, you need tons of examples.
Tons. And as top researchers like Andrew Nag or Yoshua Bengio have said, we simply can't label everything in the world. It's not scalable. It's a bottleneck.
What else?
Well, current systems often lack what you might call deep understanding. They don't really go below the surface. They're brilliant pattern recognizers, but they struggle enormously with things like counterfactual reasoning, thinking about what-if scenarios.
Like, what if I hadn't done that?
Exactly. Or true common sense reasoning. Basic facts about the world that humans just know. Understanding the underlying purpose or intent behind language.
Can you get an example?
Sure. A system might learn correlations from text, but struggle with simple physical reasoning. Like if you tell it, I moved the plant closer to the window, it might not inherently grasp why that plants need light to grow unless it's seen countless examples explicitly stating that connection. It doesn't have that built-in model of the world we do.
Okay, so data dependency, Lack of common sense, anything else.
A really worrying one is their vulnerability to adversarial attacks.
Adversarial attacks, what are those?
It means deep learning systems can be tricked, sometimes quite easily, by inputs that have been subtly manipulated in ways humans wouldn't even notice.
Like how?
Well, researchers have shown you can create special patterns on eyeglasses that cause facial recognition systems to misidentify someone. Or put small, weird-looking stickers on a stop sign that make an AI classify it as, say, a speed limit sign.
Whoa, seriously?
Seriously. Or even make tiny, imperceptible changes to pixels in an X-ray image that could lead an AI to generate a fraudulent cancer diagnosis.
That's disturbing.
It is, because it shows these systems aren't seeing the world like we do. They're picking up on statistical patterns, sure, but patterns that can be brittle and easily exploited. It really makes you question what understanding means for these systems.
Yeah, definitely.
And finally, there's the issue of generalization or transfer learning. While AIs can achieve superhuman performance in very narrow tasks.
Like Go or specific image recognition.
Right. They often fail miserably if you change the task even slightly. They lack the human ability to abstract principles and apply them to new related situations.
Like the game-playing AI you mentioned.
Exactly. An AI might master a video game like Breakout, but if you just shift the paddle's position on the screen by a few pixels, its performance can completely collapse. It hasn't learned the concept of hitting a ball with a paddle. It's learned a very specific pixel pattern. It lacks that flexible, abstract understanding we take for granted.
The pursuit of artificial general intelligence, AGI.
Okay, so given all those limitations, the data hunger, the brittleness, the lack of common sense, what's the big dream then? The ultimate goal? I guess that's artificial general intelligence, right? AGI.
That's the term, yeah, AGI. Or sometimes you hear human-level AI or strong AI. It's the idea of a machine with the same breadth and flexibility of intelligence as a human being.
A true thinking machine.
Essentially, yes. And the classic benchmark, though maybe a bit outdated now, is the Turing test.
Ah, the Turing test, where a human talks to a machine and a human and has to figure out which is which.
That's the one. Proposed by Alan Turing way back in 1950. Could a machine carry on a conversation so convincingly that you couldn't tell it wasn't human? It really kicked off the modern field, arguably.
So when might we actually get there? To AGI. I hear predictions that are all over the map.
They really are. It's fascinating, actually. You have someone like Ray Kurzweil, a well-known futurist, predicting human-level AI around 2029.
That's really soon.
Incredibly soon. Then you have others, like robotics expert Rodney Brooks, who thinks it might be closer to the year 2200.
Wow, that's a difference of almost 2 centuries.
Exactly, and then people like David Ferrucci, who led the IBM Watson team, maybe somewhere in between, suggesting systems that can learn autonomously might emerge within the next decade or so, which could be a stepping stone.
So why such a massive disagreement among people who are, experts in the field?
Well, Kurzweil, for instance, argues that people like Brooks are thinking linearly. They're looking at past progress and extrapolating, but failing to account for the exponential nature of technological growth. He calls it engineer's pessimism.
So Kurzweil thinks progress will speed up dramatically.
That's his argument. Others are perhaps more focused on the sheer difficulty of the remaining hurdles, the things AI can't yet do. It highlights a fundamental uncertainty about which challenges are just engineering problems and which might require entirely new scientific breakthroughs.
Okay, so what are those big hurdles? You mentioned common sense earlier.
Common sense is arguably the biggest one. That vast ocean of background knowledge about how the world works that we humans mostly pick up effortlessly, almost from birth.
Babies seem to know things aren't solid one moment and gone the next. Basic physics.
Exactly. There seems to be some inherent structure for learning that we're born with, not just a completely blank slate that current AI models often resemble. Remember Douglas Linnett's Psych project?
Vaguely. That was trying to write down all of common sense.
For decades, literally, a massive effort to manually encode millions of common sense facts and rules into a database.
And did it work? Did it create AGI?
Well, no. It resulted in some useful but narrow commercial applications. It didn't achieve general intelligence. It just underscored how incredibly vast and interconnected common sense knowledge really is and how hard it is to formalize.
Okay, so common sense is one hurdle. What else?
Abstraction and analogy making. Our ability to see deeper patterns, to understand concepts beyond surface appearances, and to map knowledge from one domain to another.
How do you even test that in an AI?
There are specific kinds of visual puzzles designed for this called Bongard problems. They present two sets of simple diagrams, and you have to figure out the abstract rule that distinguishes set A from set B.
Okay.
Humans are incredibly good at these, scoring near 100% even with novel problems. But even powerful ConvNets, today's best image recognition AIs, when trained on tens of thousands of Bongard examples, perform only slightly better than just random guessing.
Really? That's a huge gap.
It's a profound gap. It suggests current deep learning methods are fundamentally missing something about how humans generalize and form abstract concepts.
Wow. Any other major hurdles?
Causal reasoning is another big one, championed particularly by Judea Pearl, a Turing Award winner.
Cause and effect.
Exactly. Understanding why things happen, not just that they tend to happen together. Pearl argues that current machine learning, especially deep learning, is mostly stuck at the level of correlation, finding statistical associations in data.
Curve fitting, as he calls it.
Right. He sees it as sophisticated curve fitting, but lacking the ability to reason about interventions. What happens if I do this? Or counterfactuals, what would have happened if I hadn't done that? He believes this causal reasoning ability is essential for strong AI, even if it's not the whole story.
It's not just about more data then.
Yeah.
Some people seem to think that if we just feed these systems enough information, common sense and abstraction will just sort of emerge.
That's a hypothesis, the idea of emergent intelligence. But honestly, the current scientific evidence doesn't really support that for things like common sense just popping out of bigger data sets and current deep learning architectures.
So maybe we need different approaches.
Many researchers think so. Jan LeCun, another deep learning pioneer, emphasizes how much babies learn just by observing the world through unsupervised or self-supervised learning without needing explicit labels for everything. He sees cracking that getting AI to learn rich models of the world just through observation is the main hurdle now.
Okay, so what are the paths forward then, if deep learning alone might not be enough?
Well, Yoshua Bengio uses this nice metaphor. He says, we've climbed a significant hill with deep learning, made amazing progress. But now, from the top of this hill, we can see other, maybe even bigger and more challenging hills ahead these limitations we've been discussing.
So new challenges become visible.
Exactly. And the consensus among many experts is that deep learning, while incredibly powerful, is likely just one tool in the toolbox.
We need other tools.
Probably. Many believe that continued progress will require integrating ideas from other spheres of artificial intelligence, maybe hybrid systems.
Hybrid, like combining deep learning with other AI techniques.
Right. Perhaps combining deep learning's pattern recognition strengths with older symbolic AI approaches that are better at logic and explicit reasoning, or integrating probabilistic methods that are good at handling uncertainty. Geoffrey Hinton, another giant in the field, has also suggested that maybe true advanced intelligence won't come from one giant AI brain, but from communities of intelligent systems learning collectively from vast distributed data.
Lots of different ideas floating around then.
Definitely. There's no single agreed-upon path to AGI right now.
Societal impact and ethical considerations.
Okay, let's shift gears a bit. Beyond the technical challenges, everyone worries about the impact on society. And the big one, the one you always hear about, is jobs. Is AI going to take all our jobs?
That's the million-dollar question, isn't it? Or maybe trillion-dollar. Look, analysis from places like the McKinsey Global Institute suggests it's more complicated than just mass unemployment.
How so?
They predict AI will certainly lead to some jobs loss, tasks being automated, but also significant jobs gained, new roles created by AI or roles augmented by AI, and potentially a net positive impact on overall employment in the long run.
Is there a historical parallel for that?
Well, think about the Industrial Revolution. Huge disruption. Many traditional jobs disappeared. But ultimately, it led to far more jobs, increased productivity, and widespread prosperity, even though it was painful for many during the transition. Or more recently, think about the app economy. Who predicted jobs like app developer or social media manager 20 years ago? Technology creates new needs and new roles.
Okay, that makes sense. But which jobs are most likely to be affected now? Is it just low-skill jobs?
Not necessarily. It's less about skill level in the traditional sense and more about the nature of the task. Jobs involving highly repetitive tasks, whether physical or cognitive.
Like data entry or assembly line work.
Exactly. Or routine data collection and analysis. Those are susceptible to automation, even some highly paid jobs, if they're sufficiently repetitive.
And which jobs are safer then?
Jobs that require complex human judgment, managing people, creativity, emotional intelligence. Also, physical work in highly unstructured, unpredictable environments.
Mm.
Think plumbers, electricians, caregivers. Those are much harder to automate fully.
So the key is adaptability, learning new skills.
Absolutely critical. Continuous education, reskilling, retraining, these are going to be essential, both for individuals and for society as a whole, to navigate this transition successfully.
Okay. Beyond jobs, though, there are some really deep ethical questions AI throws up, aren't there?
Oh, huge ones. And we're only just starting to grapple with them properly. Bias is a major concern.
Bias in AI, how does that happen? Isn't AI supposed to be objective?
That's the misconception. AI learns from data. And if the data generated by humans reflects existing societal biases, racial, gender, socioeconomic, then the AI will learn and often amplify those biases.
So it learns our prejudices.
Precisely. As Fei-Fei Li, a prominent AI researcher, put it, if that data is biased, our machine learning outcome will be biased. And she warns that can have potentially fatal implications in sensitive areas like hiring, loan applications, criminal justice, or healthcare.
Wow. Okay, bias is one. What else?
Privacy is another huge one. Think about facial recognition technology becoming ubiquitous, or AI systems constantly collecting and analyzing our personal data. There's also the concern that AI could lead to an even greater concentration of power,
How so?
because developing and deploying cutting-edge AI requires immense resources data, computing power, specialized talent. That tends to favor large corporations or governments, potentially increasing inequality and centralizing control.
Given all this complexity, bias, privacy, power, how on earth do you regulate AI? It seems almost impossible.
It's incredibly challenging. Interestingly, many AI practitioners themselves actually support regulation. They see the potential risks.
Really? You'd think they might resist it.
Some do, but many recognize the need for guardrails. However, there's a strong feeling that regulation shouldn't be designed solely by AI researchers or tech companies. It needs broader input.
It's a societal issue, not just a technical one.
Exactly. It's a societal and political question. One approach, suggested by Jan LeCun, among others, is maybe not to try and regulate AI research itself that could stifle progress, but rather to regulate specific AI applications based on their potential impact.
So regulate self-driving cars like cars. Regulate AI in medicine like medical devices.
Something like that. Focus on the domain and the risks within that domain,
Right.
rather than a blanket regulation of AI as a technology.
Okay. And then there's the really big, maybe science fiction sounding concern, the control problem. Superintelligence going rogue.
Right. The idea, most famously articulated by Nick Bostrom, is that if we create an AI far more intelligent than humans, superintelligence, could we ensure its goals remain aligned with ours? Or could it develop objectives that are unintended and potentially catastrophic for humanity, even if it wasn't initially programmed to be malicious? It's framed as a potential existential risk.
But not everyone agrees it's an urgent problem.
No. Andrew Ng, for example, has famously said worrying about AGI evil killer robots today is like worrying about overpopulation on the planet Mars. He sees it as a very distant concern and thinks we should focus on the tangible AI problems we face now, like bias and job displacement.
So split view there, too.
Definitely. But there's a related issue that many experts agree is an urgent concern: autonomous weapons.
Weapons that can select and engage targets without human intervention.
Exactly. Lethal autonomous weapon systems, or laws. Stuart Russell, another leading AI researcher, warns forcefully about their scalability. Unlike nuclear weapons, which require rare materials and complex infrastructure, autonomous weapons could potentially be mass-produced cheaply. He argues a small number of people could launch millions of them, making them effectively weapons of mass destruction in terms of their potential impact.
That's a chilling thought.
It is. Jan LeCun, while he disagrees with the specific mass destruction label, fully acknowledges the severe risks and agrees there's an urgent need for international coordination, maybe even treaties, to prevent their development and misuse. It's a much more immediate ethical nightmare than hypothetical superintelligence for many.
And just finally, what about this idea of an AI race, especially between, say, the US and China? Is it really a competition where one country wins and others lose?
That narrative is certainly popular in the media. But again, some experts offer a different perspective. Andrew Ng suggests it's maybe less of a zero-sum race and more like the electricity race a century ago. Meaning electricity was a foundational technology that ultimately benefited every country that adopted it. He sees AI similarly as a general-purpose technology that will lift all boats, so to speak. Demis from DeepMind also points out that there's actually still a huge amount of global collaboration and open publishing among AI researchers worldwide.
So maybe more collaboration than competition behind the scenes.
At the research level, often
Yeah.
yes, though geopolitical and economic competition is obviously still a factor. Outro.
Wow, what an incredible journey we've taken in this deep dive. I mean, from the absolute basics, the math underneath machine learning, all the way through the deep learning revolution that's changing everything, then peering towards that ultimate goal of AGI, and finally wrestling with these massive societal and ethical impacts.
It really covers a lot of ground, doesn't it? And I think what really stands out, or at least what stands out to me, is this contrast.
Mm.
We have AI systems that are superhuman at certain narrow tasks, recognizing patterns we can't see, but they still fundamentally lack these core human abilities, real common sense, that flexible abstraction, even just the humility to say, I don't actually know, when faced with true uncertainty.
Yeah.
And it reminds you that knowledge, well, it's most valuable when it's truly understood and applied wisely. And hearing different perspectives, like we've discussed, really helps build that deeper understanding.
It really does.
Okay.
So here's a thought to leave you, our listener, with. If the grand aim is truly human-level intelligence, AGI, and yet our most powerful AI tools today still stumble on things that are basic for us humans, like common sense or knowing when they're out of their depth, what kind of breakthrough is it going to take? What unexpected, maybe fundamentally different, perhaps even more human-like insight will be needed for AI to finally make that leap?
And maybe building on that, a question for you to consider is this. As we continue to build these increasingly powerful and intelligent systems, how do we as individuals, as communities, as a society, make absolutely sure we're also building the ethical guardrails, the robust human oversight, the societal structures needed? How do we ensure these incredibly powerful tools truly serve humanity's best interests and don't end up creating a whole new set of problems we didn't foresee?
A lot to think about there. Definitely food for thought. Thank you so much for joining us on this deep dive into the world of AI and machine learning. Keep learning, keep asking questions, and we'll see you next time on The Deep Dive.